So what is a swerve drive? Basically, all a swerve drive is just a drivetrain that allows the drive wheel to move completely freely in a 360 degrees. And this can be achieved by having the motor itself be on the drive wheel and having the drive wheel pivot. However, I don't think this is very optimal, and I feel this way because you could just have both motors stationary, your drive motor and your pivoting motor. And this is an example of just the optimal swerve to use. But there are some drawbacks with using a swerve. Cost is the main one because it's very expensive to get modules, along with the programming is quite difficult, which is why I want to make a swerve that is very cheap and simple to program. And which is why in today's video, I'm going to be showing the process of how I made my swerve so cheap, efficient, and very compact. And the goals I'm going to set within this project is to have open source electronics anyone could buy, along with just a simple design that anyone could replicate. Because I won't be just posting this CAD for anyone to use. However, I want to make it very simple and easy to, for anyone to replicate at home. So now for the actual performance of the robot, I want it to be able to have the drive wheel to rotate completely independently in any direction. So beyond 360 degrees, just spinning indefinitely forever. So this means I can't use just a motor on the drive wheel. I'm gonna have to have the both motors stationary. Over here is the actual whole pod without the triangular chassis. So let's isolate this real quick, just so I could show you guys how this works. So there's the shaft here that runs from a pulley all the way down onto these two gears. So there's this gear, the spur gear, and then this other gear here. That all goes down to here, to this bevel. And this bevel rotates the wheel itself. So that's just like the basic idea of how this works. This is the bearing itself that it rests on. So the whole swerve rests on just one singular bearing that's sandwiched between this 3D printed piece and that 3D printed piece for the inner trace, and then the outer trace is sandwiched by 4 bolts right here. These will be these will have like flat bottoms. Right now it's just the hex bolt that I have imported. And then this is all driven by, like I said before, this one servo, which is actually just there to rotate only the pod. And then this one is just a regular DC motor that is able to drive the wheel, like I showed before. And over here is how all the 3D printed pieces look, isolated. So there are a bunch of spacers that I use that are 3D printed, like these ones here. That's just to keep everything centered and properly aligned, as well as this one to make sure that the gear that rests right here doesn't move upwards or downwards when it's there. And then the wheel is also 3D printed along with all of the parts that hold the pod together. And now let's get into the time lapse. So now that you've seen how this swerve is built, I want to talk about the motors that I use. So I specifically chose this servo from Axon because you're able to convert the servo itself into a regular DC motor with encoder. And you do this because of this programmer right here. So you're able to plug into the servo into, not that port, this port. And you're able to set it to a continuous rotation servo. So the signal that the servo actually picks up that would previously be used for position is now used for direction and speed. And it's cool that you're able to just make it into a CR servo. However, it's been done before. What's really special is that it has an absolute encoder built into the servo itself. So I'm just able to always read and track the position of this shaft right here. So if I were to do this project without this type of servo, I would have to either get another continuous rotation servo or a DC motor and then have a separate encoder just on the drive shaft, which isn't that bad to do. Like a lot of teams do that, especially in FRC. However, it's just another point of failure and another thing you have to worry about when you're building your swerve. And just from a design standpoint, this can't move as fast as a regular DC motor with encoder. However, I don't need that speed. I just need it to reliably get to its set position in a decent amount of time, which this can do. And it just allows me to simplify the whole build process because I can just pop this into the swerve instead of having to put a whole motor with encoder on. And speaking of design, I haven't really talked too much about the design of the chassis. So I talked about the pods themselves, but I only have 3 here. Normally you would have 4. And the reason why I chose 3 is because I wanted to try something new. I wanted to do it in a Kiwi style orientation, which is similar to what you use normally with Omni wheels. but I'm using swerve pods instead. That's why it's in a perfect triangle. All right, so now I want to talk about electronics because the actual robot hasn't changed at all mechanically. So right here, I have the touchscreen, which is just the interface that I'm using for the Raspberry Pi that I'm using to control this robot. And it just acts as like a monitor, basically. So I'm able to debug code on the go. Over here, I have this breaker, which is just, I'm using it mainly as a switch, but it also regulates the amount of current that could be pushed through. So it caps out at 20 amps, and I'm just able to do it like that. Now, on the inside, now these are 10 amp motor drivers that I've switched from these, which are, this one is a 2 amp motor driver, because a 2 amp one was quite bad for what I'm doing. The motors, whenever I would like push current through it, even at like full speed or the maximum amperage that this driver could output, the motors wouldn't move too well. It would be around like, from what I've seen, 33% of the speed that these drivers can output to them. I think it's more of just an efficiency thing rather than like a rating issue, because in theory, these should have worked, because these motors don't consume more than 2 amps with the current configuration I have now. The max I've ever seen, even with these drivers, was like about 6 or 7 along all 3 motors, which is quite a lot because normally they consume about 5 under because there's not much load that like it's trying to push. And now I'm going to talk about this servo board here. This is just a hat that attaches directly onto the Raspberry Pi. It's externally powered with 24 volts, and it converts it back down to 5 volts for these servos, or I think it's actually 7 point something, 7.2 I think. So these servos, and these servos also have the 4th pin, like I said before, for encoder positions, which the board is over here. It's hard to see because there's so many wires, but you see these little wires here, those go to that board. And basically what that allows me to do is, like I said before, use PID to control the servos instead of using set positions. So I'm able just to have the servo approximate, or not approximate, I'm able to have the encoder know the servo's position always. And then whenever I want it to go, let's just say, from like 50 degrees to 20 degrees, as it approaches 20, it'll slowly ramp down and slow down. And then what controls all of these parts, like I said, was a Raspberry Pi. So this Pi takes 5 volts from this USB, I don't know what it's called. I think it's like a converter, because it converts 5 volts, no, it converts 12 volts to 5 volts, 3 amps, which is what the Pi is rated for, I'm pretty sure. And that just simplifies the process for me, because I'm able just to tap into the 12 volt battery to control everything on here. But however, it comes with some issues, because if there's a really big voltage spike or dip, the Pi has a chance of turning off and just completely browning out everything here, which is not good. But so far I haven't had no issues with it, and I've also had fail safes within my code to say, if you see a huge dip or if the Pi loses a lot of power, just shut off the whole code, and then I'll have to reboot it and then just start it over again. So now that the actual build of the robot is good, along with the electronics, I want to talk about programming. So I'm going to be using PID for each of the pods, and there's going to be a separate controller on each one. And this is because just of tolerances. Each pod is slightly different. Not different enough to where like a human could see it with the naked eye. But when you're actually like rotating the pods, you'll see it jitter if you just use one PID value for all 3. And then servo-wise, I have another piece of code that basically allows it to wrap the position, meaning that if I was perfectly at 90 degrees and I wanted to go to 270 degrees, I wouldn't have the servo move 180. I would just have the motor's polarity flip. And then all the positions are just based off of where the controller's joystick is. And then I also have a code for turning. So the part of the robot with the one pod on the front, that will just be at 90 degrees, and the other 2 will be at 45 and 45. And then the motors will just spin in certain directions to allow for a right or left turn. And that's just like the generalization of how the code in theory will work. And a lot of teams who use swerves for competitions will not program it this way. They'll use like a lot more math and just optimize it as much as they can, because if their drivetrain breaks, or if not breaks, but if it's just inefficient compared to another team's, they will lose the match, or there's a very high chance they will. So at this point, the whole robot is done. So there are a few videos of it driving around. And I've also programmed an autonomous mode for this robot, basically just allowing it to run on its own without any human interaction. So, go this way, then up there. And this is all random movements right now, as you can see. And this is just how that looks when it's running. So it randomly picks a direction and then it just goes to it. And those clips were from when I went to a competition. I wasn't competing with this robot, but other teams were competing there, and I allowed them to just drive it around and test it. And I learned a lot from this. So from what I've seen, just during that time, is that the mechanical and the electrical portion of the robot is fine. Like the drivers for the motors that I thought would be hot weren't. They were actually quite warm, which is really good. Mechanically, it held up fine. Nothing really broke on it. There was also, I didn't see any issues with the 3D prints. Like, I would thought that the printed pieces would break, but they didn't. And since the mechanical and electrical portions were good, those will not be changed. However, I've seen a major issue with the robot, and it just comes down to programming. This really just comes down to the way the pivoting, like the pivot portion for the wheel actually just was programmed. It wouldn't always like go to its set position properly, and occasionally the motor's polarity will flip out of nowhere, just making it unable to be driven very like efficiently. So a choice I made when I was programming this is to keep it robot centric, meaning that the robot uses itself for its relative orientation. However, a lot of teams that use Swerve use field centric, and just to keep it like really simple, when you're running a robot centric robot, the front of the robot is always forward. When you're running a field centric robot, even if your robot is like shifted like maybe 45 degrees and you push forward, it'll move sideways and it'll just go forward in the absolute direction. Hopefully I'll be able to fix this and make it field centric, because it's just way nicer to drive it that way. But for now, this project is completely done. And I feel this way because the Swerve itself is just very simple to build. It's also quite simple to repair if something were to break. It's also relatively cheap compared to other options. And aside from the mechanical bits, the electronics are also, I feel like, really well done, since it's anyone could buy those motor drivers, anyone could buy the board that allows for the absolute encoders to be read by the Raspberry Pi. The Raspberry Pis are very accessible now. Like, you could get one for I think around like $60, and the hat itself for the servos are like $40. So the electronics are quite expensive. However, compared to other options that you would have to use before, like maybe like a controller from Rev Robotics, which is upwards like $300. This is like a third of the cost, and it works just as well. And due to my goal being met, I'm just gonna wrap it up here. Thank you for watching, and hopefully you learned something new.